My name is Alan, and in this video I would like to present a summary of the article Artificial Recharge of Groundwater, Hydrogeology and Engineering by Dutch scientist Herman Bouwer. Artificial recharge of groundwater means that we divert various sources of water to be stored in the ground. We may also assist the infiltration of water to reach the aquifer. Depending on local geology, we can use three types of recharge systems. Surface infiltration through typically large land areas. Vadose zone infiltration through ditches or canals, which is a way of increasing infiltration surface area using less land area. These have a tendency to clog. And infiltration wells, also called interception wells. These are typically used where surface infiltration is low or there's a lack of available land surface. It may also be that aquifers are deep or confined. Climate change increases the probability of extremes in weather, such as more frequent droughts and excessive rain. This means that artificial recharge is increasingly important because we can store water in periods of abundance for use in periods of scarcity. Depending on local climate, specifically the amount of precipitation and evapotranspiration, urbanization may be seen as preventing water from reaching the ground or as a collector of water that can be diverted to artificial recharge. Other objectives of artificial recharge are to reduce seawater intrusion and land subsidence due to declining groundwater levels. The traditional way of storing water has been with dams. However, good dam sites are becoming scarce. In addition, dams have various disadvantages such as evaporation losses, disturbing of waterways and wildlife, and increased risk of malaria and other diseases, none of which are an issue with underground recharge that has no open surface. Another obvious advantage is the volume that can be stored without taking up space above ground. Water sources for artificial recharge include water from perennial or intermittent streams, storm runoff, draining from fields, and sewage treatment plants. There's a widespread reluctance to drink water from treated sewage, and my personal favorite advantage of groundwater recharge is the ability to turn eau de toilette, not that one, this one, into spring water just by passing through a hole in the ground. It's almost like magic, or as it is also known, geopurification. As the water percolates through layers of soil, sand and gravel, pollutants and contaminants are filtered out, broken down by microorganisms and absorbed by the soil. The paper aims to achieve a comprehensive overview of the design and management of artificial recharge of groundwater, including generally detailed descriptions. The objective is to enable readers to understand the key principles and practical considerations involved in designing and successfully managing artificial recharge of groundwater. The paper is very information dense, covering theoretical calculations as well as specific instructions such as how to pack the soil around the infiltrometer cylinder. Whilst the report does not explicitly describe research methods or experiments, it does discuss considerations for designing and implementing artificial recharge systems. These factors include the permeability and hydraulic conductivity of the soil, which are crucial for determining the infiltration rate and the potential for clogging. The geological formations and groundwater flow patterns in the area need to be understood to ensure that the recharge water is directed towards the desired aquifer. Precipitation, temperature and evaporation rates can influence the recharge rate and the potential for water losses. The quality of the water being recharged needs to be assessed to ensure that it does not contaminate the groundwater. The most emphasized topic of the paper is the quality of recharge water. There are two reasons for this. One reason is to reduce clogging of the infiltration surface. Clogging happens to all designs and will over time cause reduced infiltration rates, which should be considered in the calculations of the required surface area. All depending on the source of the recharge water, it may contain various pollutants picked up from paved areas, irrigation water, sewage, and many more sources. There are three categories of clogging material. Solids suspended in the water, such as clay and silt particles. Precipitation of dissolved minerals, such as calcium, magnesium, and iron. Accumulation of algae and formation of biofilms. The other reason is to protect the quality of the existing groundwater. Groundwater used for drinking is usually considered the highest quality and often pumped from sources where the water is from a time before pollution by industrialization. In the US, the water used for well injection is usually treated to meet drinking water quality standards and is often chlorinated. Effluent for well injection should at least receive tertiary treatment to remove suspended solids, protozoa, and parasites by filtration. Bacteria and virus are removed by chlorination, UV irradiation, or other disinfection. Another way to describe the findings of the report is to present the structure as a process with three main steps. Conceptualize the problem, that is, describe the situation and understand the volumes involved, where they come from, the water quality, and what should be done. Find a solution. By use of soil maps and hydrogeological reports, promising sites can be selected and the textural classification can be evaluated in terms of hydraulic conductivity. Calculations can predict the volumetric infiltration rates, based on which wet infiltration tests should be performed by means of infiltrometers. Evaluate the solution before any major construction work is initiated. Especially in areas with large differences between winter and summer temperatures, viscosity effects alone cause winter infiltration rates to be as low as about half of those in summer, and there are so many variables that are hard to predict that the best way to get adequate design and management information for a full-scale project is by installing a few pilot basins of some 20 by 20 meters and operate them for at least a year. The paper concludes that artificial recharge is a valuable tool for managing groundwater resources, particularly in areas with limited water supplies or where groundwater quality is declining. Successful implementation of artificial recharge systems requires careful consideration of factors such as soil properties, hydrogeology, climate conditions, and water quality. The paper also emphasizes the importance of proper design, monitoring, and management of recharge systems to ensure their long-term effectiveness and to prevent potential negative impacts, such as clogging and groundwater contamination. The implications of the report are significant, as it provides a comprehensive guide for policymakers, engineers, and water resource managers to understand the principles and practical considerations involved in designing and implementing artificial recharge projects. The paper can also be used to inform decision-making regarding water resource management and to develop sustainable water strategies. The paper is a structured overview of important aspects to involve in the planning of artificial recharge of groundwater. And to me, as a student with a genuine interest in the subject, it was a great introduction. It's also what makes it difficult to pick the takeaways to present, because there are so many aspects to cover. The paper would have benefited from referencing a few case stories, indicating actual scope, such as the two mentioned here. Likely because the paper was written in 2002, there's no mention of the so-called forever chemicals, such as PFAS, and for the same reason, the use of artificial permeable surface materials are also not mentioned. Future research could investigate strategies for water management, considering such modern materials and the possibilities they provide. Thank you for your time.